describe it, and so on. So this is a complex problem. So we are going to do a very simple version of it, but I want you to understand that identification of load is a very complex deal. The second thing, after we have identified the load, the second thing that we are going to do is identify the critical locations where failure is expected to occur. This is a combination of science plus experience. So you can figure out where things are going to occur by just knowing some basic facts of science, and we will do some of that. We will do a little bit of this. Experience, you have to learn, and then over time you will soon learn which portions are likely to fail, which portions are not likely to fail. This is expert. This is where you call an expert. Okay. The next one, after you do this, 3 is you have to find the loads at these critical locations in terms of external loads. So this is the next step. You have to find where the loads are going to be applied, and use that information to find. This is typically what is called load analysis or equilibrium analysis if it is statics. Okay, and typically involves our usual things that you learned in statics and dynamics, you know, what is that? Method of section, method of joints, shear force diagram, bending moment diagram, all these other things. Okay, so method of sections, method of joints, shear force diagrams, bending moment diagrams, all the things that you learned in statics, this is where to use. Frame, truss, all the stuff. Summation of forces, summation of moments. I'm going to write it because I want you to I want it to jog your memory a little bit. Okay, so that's why I'm writing all of this. Summation of forces, you have to do summation of moments and all of this. So that's what you do. And then fourth is deflection analysis. This is essentially a matter of geometry. We are going to do a little bit of it. If one bar deflects this much, how much does another bar deflect? Okay, this is essentially geometry. And we have to get pretty good at this kind of geometry. Okay, the last one, finally, we have to relate forces to deflections. This is usually called material model. Okay, so you will see that I will relate the forces to deflections. Steps 3, 4, and 5 will allow us to do both stiffness and force analysis together. Sorry, strength analysis is what I should say. Then the last step, this is all math. So relating forces to deflections, and final 6, do this. This is all mathematics. Actually, mostly linear algebra. That's what this is. And the last step is find out if it will fail by comparing with standard experiments. Okay, so this is the 7-step process. Unfortunately, as I said, we are now off. You have to do a fairly detailed setup. So we can do. So these are the 7 steps. So let me reiterate. First thing you have to do is find out what the loads are, and usually this will involve quite a bit of guesswork. Okay, so you have to find out what the loads are, find out what your. So once you have found out what your loads are, the second thing is identify the critical locations where failure is going to occur. Third thing is find the loads at the critical locations, and this involves Newton's laws. And the fourth thing is use geometry to find out what are the deflection relationships. Fifth thing is relate forces to deflections. This is called material models. Sixth is do analysis to now find out how the actual forces and actual deflections of the bar are going to be, and then compare it with standard tests and experiments in order to find out whether it will fail. So this 7-step process, and the last step is the connection between your model and the experimental data. Okay, so you have a lot of things. You can see we bring in science, we bring in mathematics, and we bring in experience, and we bring in experiments. With all of this together, we will be able to do a structural safety analysis. Thank you.